I wanted to build a motor tester to replace the cord that I use. In diagnosing a motor that is bad or has a bad spot or bad insulation, one of the quick tests that I'll generally perform is take the cover off to access the terminals for the clockwise, counterclockwise, and neutral lugs, attach the hot leg to the clockwise or counterclockwise terminal, and then attach the neutral lead to the neutral lug. And there's a couple problems with this. First, it's not easy to hold on to the plug and unplug it in case you need to stop it quickly, which is not safe. The other thing is because you're using the plug that's most likely on the gate operator, you can't test voltage, and in this setup it's not easy to test current. One thing that you can do is cut away the jacket of the cable and expose the wires and use your clamp meter to clamp on one of the legs. That's easy enough, and if your cable's long enough, there shouldn't be any reason why that would be unsafe. But what I wanted to do was build a box that was just a tad bit safer and a tad bit easier to use. And what I came up with is a double gang box that has a on-off switch that always resets to off. So it's a double pole, double throw, and what I'm going to use it for is to do counterclockwise position in one direction of the switch and clockwise in the other direction of the switch. And of course, immediately when it's released, it goes back to the off position. So that takes care of a little bit of the safety aspect and a little bit more control and the flexibility of not having to test clockwise and counterclockwise, having to take this off the lug of the motor and plugging it back in. This will give me the ability to, once I've plugged it in, test clockwise and counterclockwise without having to go back to the motor. The other thing that I wanted to do was create a couple of loops, one on the high side, one on the low side, that will allow me to clamp my meter on there, or if need be, clamp 2 meters on there and monitor the current draw. So that takes care of being able to monitor the current on the high side and on the low side while the motor is operating. But I wasn't able to come up with any solution to test voltage. One thing I could do is get a cover like this and get a double outlet, or even a single outlet will do, and when I need to test voltage, which would be at the same time as current, is just plug my multimeter leads in there and then leave them in there, and then I'll have a clamp over here and or a clamp over on the high side, and that'll allow me to test voltage and current at the same time while operating it in an open and closed position, or in depending upon what I'm testing, a clockwise or counterclockwise position. I've chosen not to use this option of putting a switch over on this side and using an outlet for voltage. I thought what I would do was put some banana plugs in here. When I started looking at the banana plugs, I could not find any that I felt comfortable installing on here. It seemed like all of them would get loose and possibly expose the incoming voltage to the metal cover and possibly create a shock hazard. So for right now in this particular setup, I'm not going to have the ability to test voltage on this unit. I may come up with an outlet on the side, or may get a double gang plate that has a blank spot over here, and then I could use an outlet and then just drill a hole for my switch. But as of right now, I'm not worried about testing voltage. I'm just worried about testing current. And if I need to test voltage, what I'll do is, from my voltage source, I'll just come up with an adapter that has more than one input. One input will be used to send power to the motor, which will be controlled by the switch, and then the other input, I'll just be able to put my leads in and actually test voltage at the same time. But I don't necessarily see a need for being able to test voltage right now. I'll just use this as a current tester for the time being, and if I decide to add an outlet, I'll just buy another cover. But let's see if the principle works, and then we'll worry about any modifications after that. So as you can see, I've already painted cover that I'm going to use to install my switch in, and I've painted the box, not painting the bottom. I just painted on the sides and painted these little connectors. I don't know what they're called, but they're used to clamp a wire in there so the wire doesn't get loose. So let's start making this, and the only thing that I made a mistake on is I didn't actually put one of these connectors on this side. So I need one for my current loop here, one for my current loop here, and then I need incoming power from my voltage source, and then I need outgoing to clockwise and counterclockwise of the motor. For some reason, when I went to build this, I forgot about it. So cosmetically, it would probably look good if both of these were, one was on this side and one was on this side, so it looked like this. But that'll leave me a hole, and I don't want to go back and weld one of these tabs back on there. So what I'll do is I'll just break this one out. The paint scheme may seem a little weird, like why would you paint it, especially if it's out in the field. You're just gonna beat it up anyway. And part of the reason is just a tad bit for safety. So this is a better conductor than even having this small layer of paint on there. And I want to ground this box, and most of the time when I'm actually using it, I'll be setting it on something that's grounded, or I'll be setting it on earth ground, and I want the conduction to be best at the bottom and not on the sides and the top. It's not fail safe, but even though that's a small thin layer of paint, it does help insulate it just a little bit. And this will get beat up and scratched, so I'm not using it as my only safety measure. I'll be attaching a ground to the box, and like I said, I'll make sure that when I use it, I'll be setting it on earth ground or setting it on something that has a better ground than the path of my body. At my local electronics outlet, Tanner Electronics in Dallas, I came across some of this exterior grade power cord. So I'm going to actually use all of this for the loops, and for the current loops, and the incoming power and the outgoing power. So let's start cutting some of this and get the layout of how everything's going to work, and see what it looks like. I've got enough. I'm probably only going to use a 6-foot lead for my power source, and I'm probably only going to use a 6-foot lead going to my motor. So I've got a little bit extra to make mistakes with, and I'll cut a couple pieces off for the current loop. That's probably more than enough right there. I probably only want a loop that's about half that. I just like a loop like something like that. So I'm going to cut it back here, and we'll make one exact same length for the other side. This is a 18 gauge 3 conductor. I'll only be using one conductor for the loops. Obviously, if you pass your line and your neutral and try to take a current measurement with a clamp, they're going to phase each other out, and you'll have a reading of somewhere around 0. So each one of these is just going to have one conductor. One's going to be off from the motor, and one's going to be to the motor. So this will be high and low. Alright, so we'll just strip the insulation off these. I'm not worried about nicking the wire because I have extra wire. This is where D-snips come in handy. So now I'll just nick a little bit of the insulation, and as you can see, because it's such a short piece, I'm breaking the insulation, but I'm also pulling the wire out of the actual jacket itself. So you got to be careful not to pull too much, or you're not going to have any jacket there. So I'm going to cut it back here where the wire is solid, and I'm going to cut that. I think that should be long enough. Actually, it's probably not. Okay. All right, so on to another piece. That piece is a failed experiment. So I'm just going to break the jacket back here. I've probably nicked it, so I'm going to take my D-snips, and as opposed to casually cutting, I'm going to actually make a premeditated cut and pull, as not to pull any of the wire out of the jacket, which I just did. Okay, it's not so bad, but you could see where I nicked the wire there when I was trimming it. So that's, I know where good wire starts and bad wire stops. So I'm going to cut it back to there. Now that should give me enough wire on the inside. Just trim some of this back. And I'm using an 18 gauge wire, which would not be sufficient to run 120 volts at any high current for any long period of time. But in between each cycle, the wire will get to rest a little bit. But I'm only, the other thing is I'm not going to be using it for that many cycles. I just need to get a current reading and move on. Oh, didn't realize it had a pull string in there, and just broke the pull string. And I don't know if I'll be able to fix that. As you can see, I pulled too much of the wire out. I'm wondering if there's an easy way to solve this. I want to leave, although I'm only going to use one conductor for each side, I want to leave all three conductors in there for rigidity of the wire. So I'm going to be a little bit more premeditated with this. Like that. We're slowly but surely running out of wire. But now that I know there's a pull string in here, I'll look for it. Maybe each one of these are considered a pull string. They actually have the string inside. Oh, that one does. Let's see if this one does too. Yeah, this one does as well too. So I guess they're considering that this is supposed to be a pull string. Well, I don't think it's actually called a pull string. I'm calling it a pull string. I don't think it's actually called that. Maybe you got to put all these together and then get your pull on. That seemed like it was a little easier to do. So let's go ahead and do this one. I'm going to strip this back just enough to where I can get some of my hands on that pull string. Okay, now we got a little bit better result. That's just about right. All right, so now I'll just cut away all this excess. Get all these, I think they call them rip cords or rip strings or something like that. And I was calling it a pull string, but it's not a pull string. Maybe it is called a pull string. I don't know. Doesn't much matter. You ever wonder what that square bit's for on your 11-way or 10-way or whatever it is? This is what they're for. These screws. I'm just fitting it right now. I don't plan on tightening any of these down until I've made all my connections. Alright, that's a little bit smaller than I wanted it to be, but I think that'll be okay. I'm going to go grab a clamp and see what it looks like. The way that I'm going to be testing it is on the ground like that, and I think that's fine. think like that will be okay. That's what my theory is I want to have, granted, this won't be the most accurate reading. It'll probably be more accurate somewhere around that neighborhood. You're supposed to put the conductor equal space to get the most accurate reading in between these two lines right here. So accuracy is not the priority. I just need to basically get a relatively reasonable reading. If I'm off by 5 or 6%, I think that's fine. You may only be off half an amp or so, and if it's that close to where I need to get an accurate reading, I'll just break the circuit and find out exactly if there's an issue. But for now, I just want to get a relatively reasonably accurate reading. So I think that loop is actually going to be fine. I wish it was a little bit bigger, and maybe on another revision, if this works out, I'll do it on that one. The reason why I'm using this technique of cutting the jacket and then using the ripcord is because when I cut the jacket, you'll make little nicks like that, and I need the wire to be structurally sound. So I'm just cutting back past that point, cutting that off, and then cutting this excess off, which should be fine. I'm actually going to put this back together like this. Maybe this will add a little bit of resistance, so when I rip the jacket from the other side, it won't as easily come out. Just trim a little bit of the jacket, or not trim it, but just cut a little splice so the ripcord has an easy groove to break the jacket. All right. I'll just trim off the excess. All right, just like the first one, that's how it looks. So I'll go ahead and feed it through here. Loosen these clamps up just a little bit just to make it easier to feed through here, because I will have to pull it back and push it back and all that good stuff until I get everything mounted on the switch, which I'm still not 100% sure how I'm gonna do everything, but I've got a good idea. So this side's just a little bit bigger. That's fine with me. I'll end up trimming, for example, those two conductors and these two conductors on both sides of the loop. But I'll wait to do that just in case the plan that's in my head is not what actually works out. All right, now I'm going to take my wire that's got the 120 volt 15 amp plug on it. I'm going to take that, cut 6 feet off, and feed it through this side. All right, I got about 3 or 4 feet left over for mistakes, which I've already made 2. And now I've got 6 feet of the cable that has the plug on one side and a bare end on the other. So I'll strip this back, and I've got another cable that has just 2 bare ends on it, and that'll be used to go to the motor. So we'll start with the cable that's got the plug on the end. We're going to do the same thing that we did with the other ones. This will just be a little bit easier because when we use the rip cord, we don't have to worry about pulling the conductors out. Okay, I think that should be enough right there. So now I've got my incoming power And now we'll just cut these two sides for outgoing. And this side will just get a couple of solderless terminal connectors and some shrink wrap to reinforce the wires. Shrink wrap, heat shrink. I keep calling it shrink wrap. I don't know why. All right, so that's what the box looks like before any of the wiring is done. Let's set this to the side for a second. Now let's focus on this real quick. So I have this double pole, double throw switch, and I'm going to mount it to this light switch, but as you can see, it's too big to do it. So I'm going to take a Dremel or router or something like that and route that out. I'm going to try using this sanding drum. I'm not sure how it's going to work on this metal, and I'm not sure how nasty it's going to be doing it on the inside, but I only need a little bit, so wear eye protection. And let's see, I just need a tad bit off of each side, and I think I can get that. Let's see what we come up with. Well, it looks like that's going to do it. So this plate will cover that. First, take off my sunglasses, and I'm gonna run this nut all the way to the bottom. I wonder if I could take this off altogether. Let me see. And the reason why I want to take the nut off or run it to the bottom is simply because I need as much depth as I can, or as much space as I can for all the wiring. Because as you can see, this switch is pretty deep. Looks like that's going to work. There's the model number of the switch, just in case anybody's interested. I think that's going to do it. As you can see, I scratched up the on-off switch a little bit. I don't really care about that because I'm not going to use this for anything other than in the field. So cosmetically, it does not matter. Looks like that switch is going to have plenty of room in there. All right, let's start wiring everything up. Just a little recap. We've got incoming power, high side current loop, low side current loop, load. This is going to the load. So incoming, loop, loop, outgoing. Although it's not going to be in that order. It'll be incoming, out to the switch, out to the motor, and then the loop is going to be the last in the circuit. So we're going to do this low side loop is going to be the last in the circuit. So these two bad boys are going to go together. Let's cut these to about what length we need them. And then we're going to cut the white and green on the high side, white and green on the return loop of the high side. And the reason why I'm leaving those in there again is just for rigidity. And we're going to now cut the black and green on the low side, black and green on the return load side. And we are going to need all 3 conductors in there and all 3 conductors in there. So let's go ahead and size up the black ones. Let's see, we can go right about there. I can already tell this is going to be fun soldering this up. And this will be coming from the switch. Okay. I'm not going to cut that just yet. So I'm going to go ahead and start doing some soldering just to get some of this wiring out of the way and get my head straight. So I'm going to strip these back. Just twist these together real quick just to get them nice and clean. And we know that this black one is going to go here. This is going to go, this is going to be return. These 2 are going to get soldered together and they'll be down here. I'll just go ahead and strip these exactly where they're at now. Now this is probably going to be the odd part because this is actually, I'm going to use the green for the neutral to the motor, and I'm using a white over here. And the reason why I'm using green for the neutral is because I have to have 2 hot legs. Of course, they're not going to be running simultaneously. One is going to be hot when the switch is up, and the other one is going to be hot when the switch is down. Therefore, being clockwise or counterclockwise, let's just call this clockwise for now, this one will be clockwise or vice versa. It's not really going to matter when you go to test whichever, as long as you put these on L1 or L2, so your line level clockwise or counterclockwise, as long as you put one on the other and not your neutral, you're good to go. Okay, and this was going to go to the switch, so I'm not going to remove as much insulation. Just going to remove a little bit because this will get a some heat shrink and a solderless terminal connector. I have some 90s for these connectors that are going to go on here, but I don't have a crimper that works all that great on this small of a jacket. So it may even take a special crimper. I would imagine you could do it with you know, a pair of pliers or something like that, but I want to make sure that this connection is good. So that would actually be kind of cool right there. It would fit just perfectly, but I'm going to use these, the straight ones, and put a little bit of shrink wrap on it, heat shrink on there, and then just crimp them on there. Now that I put this small shrink wrap on there, heat shrink on there, I think that's going to be too small. It's not going to go around there, and I need it to go around this as well. It looks like it's a little too big for the wire, but it looks like that'll fit the connector okay, and we'll just apply a little extra heat to it to get it to fit. So I'm just using these not so much for insulation, but to add a little bit of rigidity to the wire. So I'm probably going to need about that. And I'm going to go ahead and, where'd it go? Oh, here it is. I'm going to go ahead and crimp this. In case you've never used this trick before, it's not uncommon that I see people put the connector on there like that and then try to grab your gun and put it in there and then make sure hopefully everything's straight. And that works. One of the tricks I like to do is just barely put it in there. Don't apply more pressure than you need to hold it. Get it straight, square, however you need it. And it makes it just a tad bit easier when you're crimping it. So, all right, looks like that's pretty good. And that's how it's going to eventually look. I'll just have to get the heat gun out and shrink that. So I'm going to trim these back a little bit. These are also going to get solderless terminal connectors. So I just trim those back just about 5/16, quarter inch. It actually does make a difference, but as long as you stay within those little guidelines, I think you're okay. So again, we're going to crimp this. That one's probably a little too long. It just prevents the insulation from going in as far as you need it to go. And you may not have enough of the back part to grab onto the insulation. Again, these are going to the motor from our switch. Just want to get as much of the conductor in there as possible. Because this is a thinner gauge, I need all the material I can get. All right. Okay, so these are going to go to the switch. That may be a little long, but that'll be okay. I'd rather have a little bit more than a little bit less. And you can already see the mistake that I made based on the fact that I do want a little bit of heat shrink on there. So the fact that they were a little long may be okay. I'm going to go ahead and cut the rest of these. I'll probably need more than that, but let's get them about the same size. Strip these back, and of course I'm stripping it too far back. That's okay. Forgot what I was doing there for a second. Strip it like that, twist them together. It'll make it a little bit nicer cut when you go to cut it with your wire strippers, if they're dull like mine are. So again, 5/16 to a quarter inch. That's again probably too long right there. And let's see if I forget to put the heat shrink on there this time. You would think that I'd do that right off the bat. All right. Going to the motor, are clockwise or counterclockwise. Going to the motor, and the heat shrink fell off. So this is going to be clockwise or counterclockwise to the motor from the switch. Come on now. Just to give you an idea where we're at now, we're going to be taking the incoming power from our outlet, and that's going to go there, and then we're going to have, you see that? And then we're going to have clockwise, counterclockwise, clockwise, counterclockwise on this side. So I'll be clockwise if I go switch in one position, and I'll be counterclockwise in the other, or vice versa, depending upon. It won't make any difference to me. I mean, we're just testing the same conductor inside the motor. The only reason why we'll want to go counterclockwise and clockwise is just to verify that there is not a bad spot one way or the other, which sometimes only shows itself one way, and we may have the load in all the way in one position and we need to back off of it or advance it in order to test the load all the way. Exciting stuff. Okay, so now most of this stuff is going to be soldered together, if not all of it. The first step is going to be tin all of these wires. Pull these out a little bit more so I can get better access to them. Let's double check and make sure we got everything soldered. Looks like I got one bad little spot there, but that'll be okay. I'll fix that when I solder these two together. Let that cool for a second. I'll use that alligator clip as somewhat of a heat sink, so maybe the part that I've already soldered doesn't break apart. when I try to get this last little bit. Pretty good connection there, and that should take care of the hot leg. I'll pull this back out just to give us a little bit of room on the other ones. That's good there. So now we'll do the neutral leg. Same type of thing, we'll just clamp them together at both ends. Son of a gun. See where I went wrong? And there's no way around that. Hopefully just under pressure alone I can get this to break apart. There we go. Get this heat shrink on there. No surprise that I forgot that. I'm running my soldering iron at about 700 degrees, which is probably a little hot, but I like to live dangerously. All right. You can see I've got it too hot. It's starting to melt the insulation. And that's what that'll look like. These will all sit on top of that. This will sit down here. So it'll be something along those lines. I think that about right there should do it. We'll just cut it back. Strip this insulation.
Here's the incoming ground, and it'll be connected directly to the chassis via this solderless terminal connector. To connect the incoming ground to the chassis, I'm using this ring terminal, so it'll be a little bit uneven. In order to compensate for that, I'm going to cut the ring off of this other terminal and place it on the other side so that the cover is level. As I'm pulling the current loops back in, I realized that I forgot to terminate this white wire. This white wire is the neutral wire that gets connected to the green wire that goes out to the motor. As usual, I almost forgot to put the heat shrink on. This is the same process as all the other ones, just soldering them together and making sure the connection's good. Now I can disconnect everything and start using the heat gun to shrink the heat shrink. I took this other box and put it underneath the box because it was getting so hot. I didn't want it to melt my ESD mat. I bought the less expensive ESD mats on purpose. These are from Velleman, I think, and I bought them because they're white and I wanted to record video, so I figured white would be better to reflect light and not absorb it so it wouldn't be as dark. But the downside is they don't last as long. I realized that the box was still hot, so what I did was take my heat gun and put it on cool and try to lower the temperature of the box that I was working on. It took a while. Now that all the soldering's done and all the terminal connectors have been terminated, I'm going to go ahead and start clamping the current loops down as well as the incoming and outgoing power. This is what it looks like when it's clamped down. The one on the right has the screws tightened down, and the one on the left doesn't. It didn't feel like there was enough room in the box with the connectors pointed straight down, so I thought what I'd do is bend them. As I was bending them on the switch, it actually started to bend the legs on the switch as opposed to the connectors. So I took the connectors off and bent them with a little bit of an angle. But after it was all finished, there was plenty of room in the box, so I didn't bend any of the other connectors after I made the revisions that you'll see in part 2. I used a little bit bigger terminal ring than I actually needed, but I wanted to span this gap without it catching on the red part of the terminal ring. If there is such a thing as upside down with these terminal rings, I mounted this one upside down so it fit just a little bit better here on the corner because of the way the cover bends at the corners. I want to make sure that there's enough room in between the bottom of the box and the way that the wires come off the bottom of the switch. Feels like, just based on pressure, that there's plenty of room, so there shouldn't be any problem. Here's the top half of the solderless terminal ring that I cut off earlier. I'm just using it as a washer to make sure that the cover is level. I'm using the same method that I used inside the box with these 3 wires that go to the motor. The black and white wires are the hot legs, and the green wire is the neutral. I'm still going to use this oversized heat shrink so I can cover the wire and the back of the terminal connector. If I had it to do over again, I'd probably make these 3 wires a little bit shorter or use 2 layers of heat shrink just to give it a little bit more rigidity. As you can see right here, I either failed to put enough pressure on the terminal or properly seat it on the actual wire. Either way, it was bad, and I caught it because I pulled on it. I think it's pretty realistic if you got this far in the project. It'd probably take you about an hour and a half if you did everything like I did it, with soldering the connectors and heat shrinking and all of the things that I think are going to make this thing last a long time. And with all the parts, the heat shrink, the solderless terminal connectors, the wire, the box, the cover, the switch, you probably only be into this thing for about 15 or 20 bucks. Now, I did make a revision, which is in part 2. That was the ability to actually check voltage. And in part 2, you'll also see that I get to test it out on a gate operator. Don't forget to like the video and subscribe.